Hi everyone. Today we're going to talk about orthogonal complements. Let us remember the relationship between perpendicularity and orthogonality. We usually use the word perpendicular when we're talking about low-dimensional space. If two vectors are perpendicular, that means that they set at 90 degrees angle to one another. This idea of perpendicular gets a little fuzzy when we try to transition into a three-dimensional space or NN space, but the same idea still does exist in higher dimensions. So to capture the same idea but for higher dimensions, we use the word orthogonal instead of perpendicular. So two vectors or planes, etc., can be orthogonal to one another in three-dimensional or an n-dimensional space. Today's learning outcomes are the following. Number 1. Understand the basic properties of orthogonal complements. And number 2. Learn to compute the orthogonal complement of a subspace. What is an orthogonal complement? Orthogonal complement, when we recall, a normal vector n to a plane is orthogonal to every vector in that plane. If the plane passes through the origin, then it is a subspace W of R cubed. Span n is also a subspace of R cubed. Note that every vector in span n is orthogonal to every vector in subspace W. Then span n is called the orthogonal complement of W. By definition, we say that vector v is said to be orthogonal to a subspace W of Rn if it is orthogonal to all vectors in W. The set of all vectors that are orthogonal to W is called the orthogonal complement of W, which is denoted by W per. There are theorems that we need to remember when we talk about orthogonal complement. Number 1, the orthogonal complement of W or W perp is a subspace of Rn. Number 2, the orthogonal complement of the orthogonal complement of W is equal to W. Number 3, the intersection of W in W perp is equal to 0 vectors. And number 4, if W is equal to the span W1, W2, and so on and so forth, then vector V is in W perp if and only if vector times W1 vector is equal to 0. For example, find the orthogonal complement of W of R cubed. We say that W is equal to span 1 to 3, and W is equal to plane with direction subspace on by vectors, and the vectors are 1, 1, 0 and 0, 1, 1. See, W is equal to x, y, z, such that x minus y plus 2z is equal to 0. We used previous theorem to find the orthogonal complement of W of R cubed. That is, W is equal to the plane with direction subspace bound by vectors 1, 1, 0 and 0, 1, 1. And B The W is equal to subspace found by vectors. That is 3, 2, 0, negative 1, 4, 1, 2, negative 2, 0, 1, and 3, negative 2, 6, negative 2, 5. Okay, for the pose test, I'm going to give you one given and I'm going to give you 1 minute to answer the question. Here is the question. Let us also try this one. Let W be a subspace of R4 with bases W1 vector and W2 vector. In the given, W1 vector is equal to 1, 1, 0, 1. And W2 vector is equal to 0, negative 1, 1, 1. We now find the basis for W perp. I'm going to give you 1 minute to answer the question. Okay, your 1 minute is up. Time is up. What is your solution? Anyone? All right. Here is the solution. So we let U vector be equal to A, B, C, and D, which is an element of W perp based on the theorem. And the theorem says U vector times W1 vector is equal to 0, which is equal to A plus B plus 0 plus D is equal to 0. And then you have U vector times W2 vector is equal to 0. After that multiplication, you get 0 minus B plus C plus D equals 0. The vector takes the form A, B, C, D, which is equal to R, negative 1, 1, 1, 0, plus S times negative 2, 1, 0, 1. These two vectors, negative 1, 1, 0, and negative 2, 1, 0, 1, are the basis for W perp. Okay, I think that's all for today. For my references, I have here the book Linear Algebra by Ron Larson, and also I posted in here an internet link, website www.educator.com/mathematics/linear algebra to know more about orthogonal complements. Okay, everyone, I think that's all for today. But before I go, let me share to you a quote from Sandel, and it says, "Mathematics allows for no hypocrisy and no vagueness." Thank you, everyone, and have a blessed day. Bye.